So, welcome back. Lecture 16, lecture 19 today. Remember, we are currently considering a model for the evolution of the universe, which is that of an exponential expansion. So the scale factor behaves like this: a of t is e to the power ht. And h is the Hubble constant. We found that there is a time variable that is more useful than the proper time of a co-moving observer, and that is the conformal time. The conformal time, in terms of the proper time, is given by this expression here. The conformal time runs from minus infinity, which is past infinity, to 0. 0 is future infinity in conformal time. Right? It's always negative. And as t goes to plus infinity, we have that it goes to 0. The scale factor, in terms of the conformal time, is given by minus 1 over h eta, which is very different from the exponential expression. It's, of course, the same space-time. There's no difference in the physics of it, but the mathematical expression is no longer exponential. Instead, we see that the scale factor now goes like 1 over eta. The scale factor is, of course, always positive. This is coming about by this minus sign and the fact that the conformal time is always negative. So as future infinity is approached, as eta runs towards 0 from the left, the scale factor blows up to infinity as it should be. Using the conformal, we plugged in. Using the conformal time variable, the Klein-Gordon equation takes this form, and remember that's the Klein-Gordon equation for the chi field, the one without friction. This is the Klein-Gordon equation for it, where the frequency squared is given by k squared minus 2 over eta squared. I dropped the mass term because later in cosmology we will also be able to, in realistic cosmology we will also be able to drop the mass term. Okay, so this omega squared is k squared minus 2 over eta squared. And as you can tell, if you look at a fixed mode k, then there will always come a time when eta is small enough so that this term dominates over that, and omega squared turns negative. Which means that the mode will no longer oscillate, but instead of e to the power of I times the time, plus minus I times the time, you will have e to the plus minus the time. So there will be an exponentially increasing and an exponentially decreasing solution. Now, let us check when this sign flip happens. So for every co-moving mode, the sign of omega squared will flip at some point in time. But when that happens depends on the mode in question. Of course, the physics behind that we discussed already. It's that every co-moving mode describes a particular wavelength that grows along with the expansion of the universe. And at some point in time, that wavelength that is described by k is going to have grown past the size of the horizon. And that's when we expect this sign flip. But let's look at the math of it. So when does this thing flip sign? At what time? How late does it have to be? In other words, how close does eta have to be to 0 coming from the left? Well, clearly, the sign flip happens when k squared is equal to 2 over eta squared. In other words, the sign flip happens when the critical time eta c is reached, depending on the mode in question, and that critical time is square root of 2 over k. just by looking at the equation of motion, we can read off that that's the critical time when the potential flips. This is actually also roughly the time when the proper wavelength corresponding to the co-moving momentum k starts to exceed the size of the Hubble horizon. So you see there are two things that are in principle independent. At a certain time, the omega squared flips sign, and at a certain time, the proper wavelength of a co-moving mode, which is expanding, will become larger than the Hubble horizon. And the claim is that those two times are pretty much the same. So let's see how that comes about. We established that the time of the sign flip is this. And now let's check when is it that the proper wavelength of a co-moving mode is exceeding the horizon size. So the proper wavelength is given in this way. What is the co-moving wavelength of a mode? The mode k has as its co-moving wavelength 2 pi over k. Right? But the proper wavelength is actually going to grow over time. In order to get from any co-moving length to the proper length, you have to multiply with the scale factor. So we take the co-moving length, 2 pi over k, multiply with the scale factor, and that gives us the proper length, the proper wavelength. So the proper wavelength of a mode of co-moving momentum k as a function of eta is given by this expression here. Now, A of eta can be expressed in terms of the Hubble constant. Let's just plug in what we know what A of eta is from just before. Remember, A of eta is minus 1 over h eta. So let's use that in our expression for the proper wavelength. So we just calculated that the proper wavelength is 2 pi over k times the scale factor, but the scale factor is 1 over h times eta. Instead of having a minus sign there and remembering that eta is negative, I just removed the minus sign and put absolute values here. Okay, so the the wavelength of the proper wavelength of a co-moving mode is changing over time according to this behavior. So wavelength blows up to infinity, of course, as you reach future infinity, which is to say as eta goes to 0 from the left. And let's ask, when is that proper wavelength as big as the Hubble horizon? Remember from the previous lecture, we calculated the size of the Hubble horizon, and the size of the Hubble horizon is 1 over h. And doesn't depend on time. We calculated in the previous lecture that when the universe is, while the universe is expanding exponentially, it has a horizon beyond which observers cannot communicate, and that horizon size is 1 over h. This is actually a speciality, it's a special case for de Sitter inflation that the size of the horizon is constant. Later we will consider a more realistic version of inflation where the universe is not expanding exponentially but a little bit slower than that. It will be power law inflation. In this case, the size of the horizon will not be constant. And that plays a role. Experimentalists are trying to measure how the size of the horizon actually changed over time during inflation. So now let's check what we get. We are setting the proper wavelength of a co-moving mode equal to the size of the Hubble horizon. Proper wavelength depends on time, but the Hubble horizon doesn't. So we are saying that proper wavelength equal to size of Hubble horizon proper wavelength was 2 pi over k times the scale factor equal to 1 over h. If we solve that equation for the absolute value of eta, we find that it is 2 pi over k, which is up to a factor of order 1, basically square root of 2 over k. So the message is that the sign flip happens about when the proper wavelength starts to exceed the horizon size. Now, in that picture so far, we assumed that the universe was strictly de Sitter space. Let us look at a more realistic case now, where the de Sitter expansion has only a finite duration. As we will see later in cosmic inflation, the assumption is that there was an early de Sitter phase, which was tremendously short, but very explosive. In any case, it lasted only for a tiny fraction of a second. So let's consider now a model of a temporary expansion, in this case simplified to a temporary de Sitter expansion, so exponential. Concretely, we will assume that the exponential expansion happened during the time interval from some eta initial to some eta final. And let's say that before that there was Minkowski space, and after that there's again a Minkowski space. Just for simplicity, we'll make it more realistic later on. So then, remember that every co-moving mode in the Sitter space crosses the horizon, and therefore its harmonic oscillator flips, when the horizon crossing time for that mode is reached, or what we called eta c earlier on, and which was minus square root of 2 over k. This is when the horizon was crossed. This is when the sign flips. But see, this time, this critical time of horizon crossing could be outside that interval. It could be before the earliest time, or it could be after the latest time of the expansion. And that means that there will be modes that never cross the horizon. There will be modes that cross the horizon. These are the ones for which the horizon crossing time is in the interval, but some may be too early, some may be too late. So overall, there are 3 classes of modes. The early ones, the ones which would have crossed the horizon if inflation had started earlier, then the ones that will cross the horizon, and then, of course, those that would cross the horizon if inflation lasted longer. So let's first look at the small modes. By the time their proper wavelengths would reach the Hubble horizon length, the de Sitter period is already over. So for them, the eta horizon crossing is much larger than, let's just say significantly larger than the end time of inflation. That would mean that this horizon crossing time, which is square root of 2 over k, would be smaller than the final time of the inflationary interval. But square root of 2 over k is also, except for a factor of 2 pi, it is also the co-moving wavelength of our mode. So another way of saying that is that those small modes are the ones that have a co-moving wavelength which is smaller than eta f. And as you will see, their quantum fluctuations do not get amplified. So modes that do not cross the horizon will not get amplified. These are the modes which have such a small wavelength that by the time that, just to review that, by the time that they would cross the horizon, inflation has already ended. Now let's look at the medium-sized modes, and those are going to be the critical ones, the ones that generated all the structure that we see in the universe around us. So these are the modes which do cross the horizon. These are the modes whose horizon crossing time is in the interval during which inflation took place. And their quantum fluctuations are going to be important in cosmology. Well, and then, thirdly, there are also the large modes. And these are modes which were already larger than the horizon. Their proper wavelength was already larger than the horizon when inflation started. So they never crossed the horizon either. They just started having crossed it already. It is not clear what role they play in physics today. The horizon, the Hubble horizon, was very small during inflation, just about 5 orders of magnitude larger than the Planck length. So those so-called large modes may have been tiny. They may have been just, 6 orders of magnitude larger than the Planck length. But they got blown up to huge lengths. And today those large modes are truly large. They would have wavelengths today of the order of the size of the observable universe. And it has been suggested that whatever the large modes did had an impact on what we now see as constants. For example, the cosmological constant. It could be that the cosmological constant that we nowadays see traces back to the behavior of very, very long-range modes, long wavelength modes. Because that would appear to us, for all intents and purposes, as something constant. Okay, so let us calculate now the quantum fluctuations in the zeta space, the amplification process itself. As it turns out, as you will see, in order to calculate, after we've set up all this quantum field theoretical framework, in order to calculate the amplification process of the quantum fluctuations, all we have to do really is solve the Klein-Gordon equation for the mode function. The only technical challenge that's left is just to solve the Klein-Gordon equation for the mode functions. And that is just an ordinary differential equation. Don't have to solve it for operator valued or anything. The framework is taking care of that. So you will see it boils down to the merely technical challenge of solving the Klein-Gordon equation for complex valued functions. So here's how this comes about. Let us look at quantum fluctuations in the zeta space. The usual ansatz is, of course, to write the chi field in terms of creation, annihilation operators, and mode functions. And we know that this ansatz will succeed. Whenever we choose a mode function that obeys the Klein-Gordon equation and obeys the Wronskian condition, then we can solve it. That's for sure. We proved that this is going to be good because this is going to ensure that the chi field obeys the Klein-Gordon equation for operators. And this is going to ensure that the commutation relations between Ein and dagger induce the proper commutation relations between chi and pi, and therefore between phi and pi, and its pi. Now, in our case, the Klein-Gordon equation takes this particular form. And in this, I still kept the mass in there. Later, we will not actually need the mass, but we can solve it with the mass, so let's leave it in there. The Klein-Gordon equation takes this form. And you see, it doesn't look all that complicated. It's just a second derivative, a constant, and then terms that have 1 over eta squared behavior times v equals 0. Now that's a little unusual here to have this 1 over eta squared behavior. See, if those two terms were absent, it would be just a harmonic oscillator. But because we have this 1 over eta squared, things are going to be a little more complicated. Now it turns out that the solution space of the Klein-Gordon equation for de Sitter space is, of course, two-dimensional, two complex dimensional, because it's a second order differential equation. And the solution space can be spanned by two Bessel functions. It's just a Bessel, it's a hypergeometric differential equation, and it's solved by hypergeometric functions, and in particular, this one is solved by particular Bessel functions that are real valued. So any solution to this Klein-Gordon equation is going to be a complex linear combination of two Bessel functions. And the two Bessel functions in question are the Bessel J and the Bessel Y functions. So one can prove or just check by plugging it into some software to check, like Maple or Mathematica. One can prove that the function u and the function u bar, they are not complex conjugates of another. Both of them are real valued, actually. So the function u and the function u bar, defined in this way, will solve that differential equation. It turns out that they are basically generalizations of sine and cosine. Now, why would they be generalizations of sine and cosine? Does anyone of you see why they would be? Why, in some limit, they have to reduce to sine and cosine? Yeah?
Because at the end, you have to get, like, if those terms disappear in the differential equation, you get the harmonic oscillator.
That's right. You see, when at very early times, eta is a very large negative number. So that term goes away, that term goes away. We're just left with the harmonic oscillator. And the harmonic oscillator has sine and cosine as fundamental solutions. And so indeed, we expect that the J and the Bessel J and the Bessel Y are reducing to sine and cosine.
For large eta.
For large eta, which is early times. Which is to say that when a mode has a very short wavelength, it doesn't know yet about what's going on in the big wild world with horizons and so on, and it just oscillates as if there was no expansion. So there is a whole family of Bessel J and Bessel Y functions, and the one that we need is the Bessel J with of order n and the Bessel Y of order n, and n is defined as the square root of 9/4 minus m squared over h squared. When there is no mass in the theory, where if it's a massless theory, this term is absent, and this is always 3/2. So it would be just the Bessel J and Bessel Y to order 3/2, but if there's a mass, then it's a little bit modified. In fact, that's already basically solving the main technical problem that we have with making the predictions of the amplification of the modes, as we will see. So what we have is that every mode function Vk, we still have to make a choice of mode function, but every mode function will be a complex linear combination of those two basic solutions to the Klein-Gordon equation. Some complex coefficients ak and bk. Now remember that to choose the mode function is to choose the a and a dagger operators that come with it. And choosing an a operator means choosing a vector or identifying a vector that's annihilated by them. So clearly our choice will be to choose the a and the bk in such a way that the a operators that come with this annihilate a vector 0 that we can identify as the vacuum vector at early times. That would be really convenient. So the strategy will be this. Let us check if modes start out in an adiabatic regime. the small and the medium-sized modes will do that. I mean, the large-sized modes will not. Remember, they start out after, they start out already so large, physically larger than the horizon, than the Hubble horizon. So they start out with inverted harmonic oscillators. For them, there is no adiabatic regime. But for the medium and the small-sized modes, early enough, they would all be in an adiabatic regime. And then we postulate that the state, let's call it omega, of the system is the state which was the adiabatic vacuum early on. Later we will argue why we expect inflation to start out with a vacuum. Couldn't it be another state? But basically, the idea is that once space-time has expanded sufficiently, whatever matter was there earlier will have been diluted away, so that we end up with a vacuum. So at the very beginning of inflation, the universe might not have been, or that part of the universe that inflated may not have been completely empty, but as soon as we had a little bit of significant inflation, we would end up in the vacuum. Okay, so we identify the adiabatic vacuum state at early times, and then we choose the VK such that they obey the adiabatic vacuum identification criterion, and we get, therefore, that mode function for which the A operators annihilate the vector that actually was the vacuum early on. And then, once we have identified the initial state as this state, and we have the complete time evolution of the field, well, then we can calculate everything. In particular, we can calculate the fluctuation spectrum at late times. And remember, that was the formula for the fluctuation spectrum. So the variance, or the square of the two-point correlator, is given by 1 over a squared, k to the third power, and then the mode function's modulus squared, where this is the mode function of the chi field. But once you take into account that it's actually divided by A, you can also view the combination of this and that as the mode function of the phi field. Okay, so now an important observation is this. We know that the mode function is the linear combination of those two Bessel functions, the Bessel J and the Bessel Y function. And we do know the Bessel J and the Bessel Y functions explicitly. Mathematical software knows how to evaluate them just as easily as sine and cosine. So what we need to do here is calculate what this is at late times, especially after horizon crossing. How big is that? Now we can calculate how big the Bessel J is going to be, because we can calculate how big the Bessel Y is going to be. And in order to calculate this particular expression, we still need to find out what the coefficients AK and BK are, right? Because then we can work out what the fluctuation spectrum is. So here it is important. Here's going to be important that we know the Bessel J function sufficiently well that we know what they do on both ends of the time scale. We know at early times there's sine and cosine that will allow us to fix the A and the BK coefficients. And at late time, we will be able to evaluate what the Bessel J and Bessel Y are, even though they're no longer sine and cosine. But we can still evaluate what amplitude they have, and the same coefficients AK and BK come in very handy now, knowing them, because then we can work out from what the Bessel J and Bessel Y are doing, what the VK is doing. And then we have our answer. So, point A was, of our strategy, let us check if the modes start out in an adiabatic regime. Well, indeed, we see from the Klein-Gordon equation that at early times, the eta squared is going to be large. Those terms are going to be absent, or very, very small anyway. And the frequency is going to be pretty much constantly just k. So at early enough times, we basically have Minkowski space behavior. V double prime plus k squared v is equal to 0. Now, let us postulate that the state of the system, omega, is the state which was the adiabatic vacuum early on, namely the Minkowski vacuum in this case. And then we choose the mode function, Vk, such that the corresponding vacuum is the Minkowski vacuum, is the early vacuum. So in other words, Vk is the usual Minkowski mode function at early times. So the Vk at early times, the mode function for our theory, at early times is just this, which is the usual mode function. Remember, I put here plus I alpha, but this is just a constant prefactor, right? It's just a phase that doesn't matter. Because if you remember in all physical predictions, we only ever have the modulus of V. So the phase doesn't matter. Let me just put a phase in there. So the mode functions for Minkowski space, as we had already in the very earliest lectures, are just like this, with or without an extra phase. And if we have a temporary de Sitter inflation, then at early enough times we have basically either exactly Minkowski space or with very high accuracy. And in the case where we neglect the mass of the quantum field, we can further simplify that and simply put a k here. Right? Omega k is really square root of k squared plus m squared. And if the mass is vanishing, then omega k is just the modulus of k. So I didn't put extra modulus bars in here, but I hope it's cannot be mixed up. This is the modulus of the mode vector k. Okay, so at early times, our mode function is going to take this form. That knowledge should allow us to determine what AK and BK are. So now let's look up what the Bessel functions are doing. Exactly how are they cosine and sine? This is exactly how they are sine and cosine, just by looking into the theory of hypergeometric functions. It turns out that the UK function, Bessel J, at very early times, at very negative etas, takes this particular form, where we have a constant there that depends on exactly where you start your time. And the U bar function, the Bessel Y, behaves like a sine. And therefore, we can now identify that the mode function, which, remember, has this form, can be expressed in terms of those two guys in the usual way, right? Cosine plus I times sine, straightforward. We obtain that the mode function is given by this coefficient times the UK minus I times that coefficient times the UK bar, which is also the same as saying that the VK function has to be this. The mode function has to be this. You see, at early times, we fixed that the coefficients are AK and BK. But these are fixed coefficients. They don't depend on time. So therefore, we can use that knowledge to express the mode function at all times in terms of the Bessel J and Bessel Y. But you see, this means we have identified the state in which the quantum field is. It's the state annihilated by the A operators that come with these mode functions. And we have the quantum field, chi, at all times, at all locations. And of course, from that, also the physical field phi. So we should be able to calculate everything now. I leave it to you as an exercise to match those coefficients. It's an important little calculation, so you may want to do it also so that you remember better what went on. So finally, we can now calculate the fluctuation spectrum that is generated by a temporary de Sitter inflation. So let's calculate what the fluctuation spectrum is at the end of the de Sitter inflationary period at the time eta final. So here's the formula again, the fluctuation spectrum, which is, if you remember, the 2-point correlator squared, or it's also the variance of the box smeared field, given by that expression here. And let's see how the various kinds of modes behave under, how their fluctuation spectrum behaves while there was a temporary exponential expansion. So let's look at the case 1 first. These are those modes K which have a co-moving momentum so large so that in this expression here, the K-squared term dominates all the time. It never flips sign. By the time this would want to flip sign, it's no longer the de Sitter inflation, and those terms are absent. So the K-squared term dominates all throughout the expansion. These modes never cross the horizon, and therefore we have that these modes have that solution pretty much all the time. Because even during inflation, that term was completely dominant over these terms. So what we have is that the vacuum fluctuations can be calculated from that mode function, evaluated at late times. So let me put it differently. The Bessel J and Bessel Y are still sine and cosine, even when inflation ends, for these very, very small modes. So the vacuum fluctuations at the end of the exponential expansion are still the same as in Minkowski space, because we still have the same functional behavior for the mode functions. So concretely, if we plug this into our formula here, where is it? Here, fluctuation spectrum. So we take k to the third over a squared times the modulus squared of the mode function, plug it in here. So here I'm writing the fluctuation spectrum, but without the square. So we just get a 1 over a, and we get a k to the 3/2 instead of k to the third power. And and then we take the modulus of the mode function. But the modulus of the mode function is just 1 over square root of k. Okay, so that's what we have for the fluctuation spectrum. And remember that k is 2 pi over L, or for simplicity, it's just 1 over L, where L is the co-moving length. So what we have here is that the square root of k cancels one of the square root powers of k to the 3/2. So we are just left with a k here, and then 1 over a. So what we get is 1 over a times L, because k is like 1 over L. But the co-moving length, which is the inverse to k, the co-moving length multiplied with the scale factor gives us the proper length. So what we obtain is it is 1 over the proper length, or proper wavelength. So modes that are so small that they never experience really the expansion of the space-time, they're too small compared to the size of the horizon, those modes have a fluctuation spectrum even at the end of inflation, which goes like 1 over the length, which is, if you remember, what we calculated for Minkowski space, 1 over L. The smaller the box, the larger the fluctuations, and the behavior is 1 over L. Or also it says that if you have quantum fluctuations, if you observe quantum fluctuations at two nearby points of distance lambda, then the correlator will blow up like 1 over the distance. Correlated, the two-point correlation function between the fluctuations. Okay, so this is the usual fluctuation spectrum for massless fields in Minkowski space. And what we see in particular is, because of this 1 over lambda behavior, what we see, very important, fluctuations which have a large proper spatial size will be highly suppressed. If the size of the box, lambda, is big, then 1 over lambda is very small. So if we look at large boxes and average the field over that, the standard deviation is going to be very small. And also the correlation between quantum fluctuations. So if, for example, we look at a box of size of, I don't know, 100 million light years, this is going to be a very, very small number. Quite independently of which units you want to use, miles or centimeters or whatever. Very small. Which is what we would expect normally, right? We don't see quantum fluctuations of significant amplitude at large scales. Even if you put a meter in there, it's still tiny. Now, case 2, medium-sized modes. These are those modes, K, whose proper size will cross the horizon during inflation. So the horizon crossing time eta is between eta initial and eta final. And the sign in that Klein-Gordon equation is going to flip, and therefore also in the frequency. Let's evaluate the fluctuation spectrum for those. Here's the fluctuation spectrum formula again. And now let's see if we can, you see, we shouldn't just trust Maple or Mathematica or a textbook on this. Let's get some intuition for what's happening. So the Klein-Gordon equation is, in this case, to a good approximation, eventually given by this. You see, the k-squared term is there, but we are looking at modes for which this term will dominate over that term. So by the time inflation is approaching its end, these modes will have this term dominate over that term. In order to see what the solution, and therefore our Bessel J and Bessel Y and our VK, what the solution is going to do, let us look at this differential equation with this term neglected. What do we get? Well, then we have to solve this differential equation. That's no longer a harmonic oscillator at all, right? Because this has a weird time dependence. However, it's not difficult to find a basis for the solutions in this late regime. Just like we would be able to solve it in the early regime, where there's only a k-squared term, and we can immediately say that it's going to be sine and cosine. In the later regime, we neglect the k-squared term, and we just have that, and we can also right away say what the behavior then is. Namely, one solution, let's call it W1. One solution is given by k modulus of eta squared. Let's just check this. So we differentiate this function twice with respect to eta, and we're going to get a k. And here we have the function v, which has an eta square in it and a k squared. And when we differentiate it, no, we don't differentiate now. We just have to divide by eta squared and multiply with 2. and then we get the same expression here as we did there. See that? How that happens? If you differentiate it twice, then you get this 2 down, right? So it's 2 times this, and then you differentiate again. In any case, you get a factor of 2. And then here you get the factor of 2 because it's already there, and otherwise it's the same coefficient. If there had been a 3, we would need a 3 over there. Okay, so that's one solution. And that solution decays towards future infinity. It decays towards future infinity because eta goes to 0. Remember, in conformal time, just a sec, in conformal time, eta comes from the left, goes to 0. This solution decays. It's very much unlike sine and cosine. It goes to 0. Yep?
Just want to make sure I'm not missing anything. If there's a 3, wouldn't the 2 derivatives make that a 6?
Oh yeah, that's right. It's a more complicated relationship, but yes, it's right. It's no longer, it's not just n going into n, it's more complicated because the n factorial. That's right. Thanks. Okay, and then let's look at another solution here. The claim is that you can solve this equation also by the ansatz 1 over k eta. Let's see what happens then. Well, we differentiate it twice, and so we get down to 1 over eta squared and then eta to the third. And if you take this term, it starts out with 1 over eta, but you get a 1 over eta squared as well. So you get also 1 over eta to the third. And you just have to check that the coefficients work out nicely. Now, that solution will blow up towards future infinity because eta goes to 0 from the left. So we have a solution that goes to 0, a solution that blows up. As we might expect, because with a harmonic oscillator that's inverted, you have, instead of positive frequencies and negative frequencies, you have a positive exponential and a negative exponential in proper time, but this is conformal time. So now let's look at the Bessel functions to see what exactly they are doing. So the Bessel functions have the following property. The Bessel function at late time, so after the k-squared term can be neglected because the potential completely flipped, it's dominated by 1 over eta squared. So after horizon crossing, the u basis function from the theory of Bessel functions has this behavior here. And the u-bar Bessel function has this behavior here. Actually, it's not the Bessel function itself, it's the Bessel function multiplied with a square root of k and eta. Remember, there's the basis functions to the solutions to the Klein-Gordon equation are not directly the Bessel functions. They are the Bessel functions multiplied with these prefactors, if you remember. Okay, so our basic solutions have this late time behavior. And what that means for our mode function, given that we can express the mode function in terms of the Bessel J and the Bessel Y, in other words, because we have the AK and the BK coefficients, we can therefore calculate what the late time behavior of our mode function is. And it turns out that only the term proportional to AK will survive, because that's the growing solution, and the term proportional to BK will not survive, because that's the decaying solution. So we can plug the late time behavior of our mode function now into the formula for the perturbation spectrum, and that's what we get. 1 over a times k to the 3/2, and then the modulus of the mode function, and that's what we have here, the modulus of the mode function. And that is to be evaluated at the co-moving wavelengths that we're interested in, or the co-moving momentum. They're just the inverse of another.
Excuse me?
Yeah?
Shouldn't the solution be pk instead of ak? Because we're using u bar, I guess.
I'm not sure which way we define the A's and the B's. Let's see. So we had, okay, so here it looks like we're using the A case for the U and the B case for the U bar, right? Okay, let's see. I think you're right. Yeah, you see from here? The BK goes with the U bar. Yeah, I'll check that. Thanks. Good. Very good. Okay. So let's collect things together, and we then find that the fluctuation spectrum is given by this expression here, where if you remember the parameter n was square root of 9/4 minus and then some mass term. It's the order of the Bessel function. And when the mass is negligible, then if you remember, n came out to be square root of 9/4, which is 3/2. So that would mean that when there's no mass term, actually this goes away, because we just have to the power of 3/2 minus 3/2. So what we then arrive at is this formula for the fluctuation spectrum of medium-sized modes. Carry forward the h. This is something to the power of 0, so it's just 1. Gamma of the order of the Bessel function, which is 3/2, and divided by pi. Now that is a curious result, because it doesn't actually depend on the size of the mode. See, there is no dependence on L or K here. It's the same for every mode. As long as the mode has the property that its proper wavelength crosses the horizon, then after it did cross the horizon, the size of its fluctuations is given by this expression here. Which depends only on the Hubble parameter. The faster the expansion is, remember h is the coefficient in the exponential that blows up the space-time in the proper time variable. The larger h is, the larger are these quantum fluctuations going to be. So the faster the universe expands, the larger are the fluctuations. But the fact that they don't depend on the size of the mode means something quite dramatic. Consider one of those modes. We just calculated that after its proper wavelength started to exceed the Hubble horizon size, this is the size, the amplitude of its quantum fluctuations. And it's going to stay that. But the mode is going to increase in its size, in its wavelength. And it could increase in its size, in its wavelength, dramatically. And that's what we will find in the standard model of cosmology. Namely that once these modes cross the horizon, and they might cross the horizon very early on. You see, the Hubble horizon, h, during the early period of inflation in the universe was probably, the Hubble horizon was, which is 1/8, was probably only 10 to the 5 times the Planck length. So any mode that crossed that horizon during the period of inflation ended up having this size quantum fluctuations even while it was stretched during inflation, perhaps even to galactic scales or much larger than that. The models of inflation, in fact, some people say the generic models of inflation, have inflation expand the universe by many, many orders of magnitude. And I don't just mean like 60 orders of magnitude, which would be the minimum. No, more like 10 to 100 orders of magnitude. So the amazing thing is that you would expect, therefore, pretty large quantum fluctuations, even at large scales. Why large? Well, large because fields maintain the amplitude of their fluctuations, according to our calculation now. Fields maintain the amplitude of their fluctuations that they have when they cross the horizon. That's when the amplitude of the fluctuations get frozen in. The actual modulus gets frozen in then. But it gets frozen in when the mode crossed the horizon, and the horizon was very small, 10 to the 5 times the Planck length. If you look at any field, like the electromagnetic field or fermionic field or Klein-Gordon field, at wavelengths as small as that, like 10 to the minus 29 meters, well, for sure its quantum fluctuations are going to be large. So these large quantum fluctuations then persist even at very, very large scales, because the modes were stretched to these large scales while having such large amplitudes. Another way to look at this is to say that those medium-sized modes that cross the horizon during inflation, are going to have their amplitudes magnified by the inflationary process to such an extent that it just compensates for what would normally be a diminishing of the amplitude. If you look at Minkowski space, the larger the size of the wavelength, the smaller the quantum fluctuations. And for a co-moving mode, in principle, you would expect the same thing to happen. At early times, it might be of short wavelength, therefore have large fluctuations. But at late times, it is of long wavelength, it should have small fluctuations. And so inflation is amplifying the fluctuations. One says that the inflation is amplifying the quantum fluctuations of a mode, but it's not amplifying it above and beyond what the mode's fluctuations would be close to the Planck length. It's just maintaining it there. It's an amplification relative to the decay that you would expect because of the usual Minkowski space behavior. So the picture that we obtain, therefore, is that after inflation has ended, we have this picture for the fluctuation spectrum. Here we have the size of the spatial size of the modes, and I'm plotting it on a logarithmic scale. So here's the logarithm of the proper wavelength of a mode. And up here, I'm plotting the logarithm of the fluctuation spectrum. And let's say here is the length that corresponds to the size of the Hubble horizon. So logarithm of 1 over h. H the Hubble parameter and 1 over h the Hubble constant, the Hubble horizon size. Now there are modes, these were the case 1 modes, which have such small wavelengths that they will never cross the horizon while inflation lasts. Those small wavelengths we calculated will have the usual Minkowski spectrum. And that means that they start out with very large fluctuations, and it goes down by a straight line of slope -1 in a log-log plot. That's the usual 1 over L or 1 over lambda behavior for modes that never get the benefit of crossing the horizon and therefore having their quantum fluctuation size frozen in. So for them, the delta phi lambda just goes like 1 over lambda. And this slope is supposed to be -1. If I could draw it better, it's not quite 45 degrees. And then there is a transition here to a different behavior. Modes that are large enough that during the inflationary period, they cross the horizon, those modes will not actually have their fluctuation spectrum diminished by the expansion, but instead the fluctuation spectrum stays the same during inflation. So that even though you might be going to larger and larger scales, the size of the quantum fluctuation stays large. So we have an amplification compared to what it would be without the horizon crossing effect. And then there are those modes, the case 3 modes, which are so large, their physical wavelength is so large, that even when inflation started, they were already larger in wavelength than the horizon size. Nobody quite knows how to set initial conditions for those guys. And what would have happened with them, we don't know. They may, because they're so large, their wavelengths could be much larger than the observable universe, much larger than dozens of billions of light years. Therefore, whatever they do might just show up in our cosmology as basically a constant, such as a cosmological constant, perhaps. One can do a preliminary estimate if what we just calculated is the seeding mechanism for cosmic structure formation, then the Hubble parameter determines the amplitude of the later observed quantum fluctuations. And so this formula here, this equation, allows us to estimate what this is, because that is measurable. Of course, there's a lot of plasma physics in it, and as you will see in the next lectures, it's really more complicated. We have to quantize gravity as well, in part, some part of the metric. At least perturbatively, we'll have to do that. But roughly speaking, if this was all there is to it, then if these translated directly into fluctuations of the cosmic microwave background temperature, then, well, there's little to fudge on this side. We can then tell how big the H would have to be. And roughly speaking, well, we do a rough estimate. The measurements of the cosmic microwave background indicate that the fluctuations of the phi field were of a magnitude that it translates, if you put all the actual numbers with their proper units in there, to a Hubble horizon of the size of about 10 to the 5 times the Planck length, which is about 10 to the minus 29 meters. And roughly speaking, this is because the size of the temperature fluctuations in the CMB is about 10 to the minus 6. So the temperature of the cosmic microwave background is about 3 Kelvin, and the fluctuations in the temperature, the angular variations, are about 10 to the minus 6 Kelvin. That's how these things translate. Also, we need to estimate not only how fast the expansion was, that tells us how fast it was, because the H is the coefficient up there in the exponential expansion formula for the scale factor. No, we also need to investigate how long did inflation last. how long was that interval from eta initial to eta final while we had that exponential expansion? And we don't really know that, but it has to last a certain minimum amount of time to account for sufficiently many modes having their amplitudes magnified so that they could feed all the structure that we see in the universe over sufficiently many orders of magnitude. And so a simple estimate says that, well, I can't mention at this point. We'll get into that in more detail in later lectures. But a rough estimate says that inflation might have lasted from 10 to the minus 34 seconds to 10 to the minus 32 seconds, which really is a very short amount of time. But with this as big as it is, this allows the universe to expand by dozens of orders of magnitude, which would allow even modes that started out at the beginning of inflation, not much bigger than the Planck length, to become of cosmic size. In practice, inflationary models favor longer and more dramatic inflationary periods. But we can't really tell how much inflation went before what we see has happened now. So inflation might have lasted a long time. Okay, that's as far as we got today. Oh, we are today 5 minutes early. Any questions? No? Okay, well, see you on Friday then.